Let's look at problem 2307, check for contradictions in equations. Here we are going to provide a traversal solution, BFS or DFS. Actually, this problem can also be solved using union find, and it's also similar or relevant to problem 990, so it's good to have a look at that problem. So here we will first go through the statement of the problem, and then we will explain the idea and the method. And lastly, we are going to give a simple implementation of this idea and method and check the test cases. First, let's look at the statement of the problem. So here we are given 2D array of strings called equations and an array of real numbers called values, where the equations specify two vertices and values specify a ratio. The ratio is the ratio between the two variables ai and bi in the equation. So we are required to determine if these equations are consistent or not. So if there is a contradiction, we are going to return true, otherwise false. So here is an important note. So because we are working with float numbers, so when we compare equality, so we mean that the two numbers are within a certain distance in their absolute value. So here the bound is 10 to the power -5. So with that said, let's look at the constraint of the problem. So here the equations has length less or equal than 500. It's not that large number. But what I want to emphasize is that the values in the ratio is strictly greater than 0. In other words, so we can consider reciprocal. In other words, 1 over value I is valid. So here are two examples and explanations. In the first example, the return is false because the relations are consistent. And in the second example, the return is true. There is contradictions as explained by this part here. So with that said, let's look at the method and idea for this problem. The method is the standard traversal method, BFS or DFS. So the idea is that we're going to use the equations and values to build a weighted graph. The graph basically stores for each vertex its neighbor and ratio. The ratio is the ratio between the vertex and the neighbor if we can impose values in the process. So the equality is interpreted by this inequality. So the actual procedure is as follows. In order to check consistency or inconsistency for the relations, we impose values to the vertices in the process. It's actually sort of hard to check in the code symbolically like in mathematics. So that's why we, in the process, impose some value when necessary. Secondly, once values are imposed during the procedure, the condition of equality check is checked for vertex neighbor pairs recursively. So that's basically the idea, the method, and the actual procedure. So next we are going to give an implementation for it. And for now, we will sort of explain in a high level. After we implement the solution, we are going to print out the weighted graph. Then you will have a clear idea about the method. So before we do the implementation, so it's good to look at Leetcode 990 to do a similar problem, I would say. First, let's do the implementation now. We will split that into different steps. So first, I would like to check equality hyperfunction. So this is specified by the problem. So it will make a simple definition, check equal. So two numbers, float numbers, whether it's equal or not, we will return whether their difference, absolute difference, is within a bound, say 10 to the power negative fifth. So this is basically a trivial step. Second, I want to build the graph. So for this purpose, I will first initialize an empty graph. So for this, I will call a collection the default dict. So if we like, we can just make the plain vanilla dictionary, but we need to treat some non-existing key in the process. So then we do the iteration. So for A, B, and R in the equations and the values, we're going to first check the self-circle. So if A equals B, so we need to know if their ratio is 1 or near 1. If check equal, so this R and 1, we need A over A is 1 or near. So if this is the case, we're going to continue the procedure. Otherwise, we're going to make a return, right? So return true because A should be near to itself. Then in the other case, if A is not B, so basically we want to update the graph. See, update the graph. So here, let me specify some container. I will use set as the container. So if A is not B, so basically we will update A by ending this tuple. So the first element is its neighbor, and the second is the ratio. Also, we want to update B, and then we add A as the neighbor, but the ratio will be 1 over R now. So that way we finished the update of the graph. Also, we also did some edge cases check. So now let's look at the DFS or BFS function, traversal helper function. So here I'm going to implement a recursion version. So let's call it depth first search. So let's see, we have current, and then we are going to check all its neighbors recursively to see if there is inconsistency or not. So basically for neighbor and ratio in graph current. So we want to check if we have already imposed values or not. So for this, basically we can introduce a variable called values, which we are going to update during the real check step. So for this, for now, it's okay, and just initialize as empty. So for neighbor and ratio in graph, so if neighbor in values, so it means we have already imposed values to that, then we are going to check if they are equal or not. So if not equal, so we are going to check the ratio, and the supposed value for this should be values the current divided by values the neighbor. And then we check the distance of this ratio with the ratio variable. So if they are not near, then this is an inconsistency. We're going to return true. So otherwise, what we want to do is that we check the neighbors recursively. So if the values haven't imposed yet, the value should be, the neighbor should have this value, values the current divided by values divided by the ratio. right? So then once we have the values for the neighbors, then we do DFS recursively. If the DFS returns a true state, basically it says that there is inconsistency starting from neighbor or in their path. So we're going to return true. And if after this for loop and the recursive calls, so there's nothing returned, we're going to return false. In other words, there's no inconsistencies. So this is the third step for the traversal help function. Now let's do the actual work. For this, because we have already initialized the values for in above, so we'll directly go for the vertices in the graph for node in graph. So we will check if node is already imposed values. If node not in values, so we're going to impose a value to start. We can impose any value. Let's see 1 for here, just a start point. And then basically we'll do DFS here, DFS as a node. If this DFS returns true, basically it says there is inconsistency, we're going to return true. Otherwise, after this for loop, we're going to return false, meaning there's no inconsistency. That's about it. This is the implementation. Let's have an overview of this. First, we implement the equality relation specified by the problem. Secondly, we are going to build a graph, a weighted graph. And in the process, we also did some edge cases check for a self-circle. Thirdly, we implemented a traversal helper function. So here the function is implemented in a recursive way. And fourthly, we do the actual check process. So basically the idea is that for each of the nodes in the graph, we want to check if their neighbors obey the racial relations. And finally, if there is no inconsistency, we're going to return false. So with that said, let's check several special cases. So here current is not, so let's change this to node. ABS here. Here we need to write it A minus B. That's it. So this basically passes the first one. Let's check the second one. Yeah, it passes the second one. So in the explanation for the method and the idea, so we are sort of in a high level. So now let's print out the graph so that we have a clear idea about the procedure. So here let's print the graph. So you see we have this LE as a node. Its neighbors are ET and code, and LE over ET is 2, and LE over code is 5. Similarly here we have ET as a node, we have code, and we have LE as a neighbor. So ET over code is 2, and ET over LE is 0.5. And similarly for code, we have LE and ET as neighbors and the corresponding ratios. Let's check the generic case. Yeah, it passes the generic case, and yeah, for this problem, basically, that's about it. Thank you very much.